Our next speaker is Ismael Morales from Oxford, I believe, talking about virtual homological invariants and profinite rigidity.
Okay, thank you very much for the invitation to speak here. First, I should comment something about the title. So when I say virtual, I guess this is well known, but when I say virtual, I don't mean virtual in the sense of the conference. But okay, when I say virtual, I mean something about finite index subgroups, right? So the point of the talk is basically to introduce some of these virtual homological invariants. What do we mean by this? Put them in some context, basically, okay, relating low-dimensional topology, some two-dimensional groups with some hierarchy, some three manifolds, and most importantly, for our motivation, to put them in context with how can they tackle questions about profinite rigidity or related. Okay, so let's begin just with this convention that all our groups are going to be finitely generated. If you want to talk about virtual invariants, another sensible convention is that they should be residually finite. But for the moment, it's not important because our examples are going to be very specific. A surface group will always mean the fundamental group of a closed surface of finite genus, let's say genus at least one. And let's recall that if the surface is orientable, then it has this presentation, this one related presentation. And if the surface is non-orientable, then it can be presented like this. So it's one relator in any case. You know that the surface is spherical, so we can compute the homology from these presentations and so on. Okay. So let me state two basically conjectures in group theory about free and surface groups that might serve as motivation for what I'm going to talk about. One is Mesanic conjecture, quite well known, that states as follows: let S be a free or surface group, let G be a finally generated residually finite group. Now, the conjecture is that if G and S have isomorphic profinite completions, and this just means that they have the same collection of finite quotients, then it's because they are isomorphic. That's basically the only case. This is okay, an example of a question about profinite rigidity. I'm not really going to talk about the theme, but to answer just why there's profinite rigidity on the title is because of, okay, the motivation of attacking this question, at least for some cases, for some groups G. And the second conjecture I wanted to mention is Melnikov, conjecture of Melnikov. There are variations of this. Maybe it wasn't stated exactly like this originally, but it's usually divided in two. But okay, the one I wanted to mention is this one, that finitely generated infinite residually finite group that has the property that all finite index subgroups are one relator, has to be of a very specific form, namely a free group, a surface group, or a Baumschlag-Solitaire group of this form. Basically, just one of the only residually finite Baumschlag-Solitaire groups. These are also examples. Regarding this conjecture, I must say Gardan, Kilak, and Logan solved, established in a positive way this conjecture. They confirm this conjecture for the case where G is 2 generated. And so the remaining case of the conjecture where the rank is 3 or more, this is right. The conclusion of the conjecture is now about free and surface groups. Now there's no Baumschlag-Solitaires. And I wanted to mention this because right, they are very mysterious, right? These two questions are very mysterious and quite open for the moment, and it's already very difficult to say something in this generality. But what I will do is to focus on a specific family of groups G, homological dimension 2, not necessarily, but let us think of that, with some group hierarchy. And in that setting, I'm going to formulate a strengthening of these two conjectures involving homological invariants. And we will see why that strengthening is true and why it implies both conjectures for those very specific groups G. Okay. Right. So let me say what is the reformulation. The ith betti number of a group G is just the dimension of the ith homology with rational coefficients. Its virtual ith betti number is going to be the supremum of all these betti numbers for finite index subgroups. Okay, and these numbers we claim should contain a lot of information about the group itself. And well, just observe that, right, finite index subgroups of free groups are again free. So the virtual second betti number of a free group is 0. And for similar reasons, finite index subgroups of a surface are again surface groups. Non-orientable surface groups have trivial second betti number, and orientable ones have second betti number which will equal to 1. So, right, the virtual second betti number is 1. Okay, and apparently this seems to be a very strong property, that we go to finite index subgroups and we don't see this second homology growing. And this is what our conjecture, probably too ambitious, but this is what our conjecture is going to try to reflect. Conjecture is the following: let G be a residually finite hyperbolic group of homological dimension 2. And suppose that the virtual second betti number is finite. Then the claim is that G is a surface group. Okay. And as I said, we're going to address this question for at least for the case when G is a limit group, or when G has a splitting over free groups and so on. We can confirm this, but in general, I mean, we don't know how difficult this is. Maybe it's just much harder than the other two conjectures, but at least our aim is to attack it in some specific cases and to put it in relation with the previous ones. But before doing that, let me precise which groups I'm going to talk about. Now, given two free groups, F1 and F2, and two words, U1 and U2, we can consider the amalgamated product. We know it's presented in this way, with just one relation. And similarly, given a free group and two non-trivial words, we can take the H&N extension, cyclic H&N extension along those subgroups. Okay, and this is basically what we should think about for basically the setting in which we are, which is dimension 2 and a finite hierarchy of free groups. Okay. So these are highlighted the examples we care about. Fundamental groups of graphs of free groups with cyclic edge subgroups. Now, we don't know anything about this. We don't know everything about these groups, but we know a lot, apparently. For example, the group G, such groups G are hyperbolic if and only if they contain no bounds like solitary subgroups. This is combination theorem of Besby and Affine. And in such case, we have very strong separability properties and very strong quasi-convexity properties on subgroups. Namely that all finitely generated subgroups are virtual retrans. Okay, so this can be precise, the saying that you take a H finitely generated, then H is going to be contained in G1 finite index, as a retract. Okay, so G1 is going to retract onto H. Okay, so these are the groups G we're going to care about, the groups which we're going to answer some of the questions I was making before. But first, let me explain to motivate the tools that are used on surface subgroups. Let me motivate those tools by saying something about a story related with three manifolds. Okay, we will denote by M closed spherical three manifold, and by G a group as before, right? Well, then, just to see examples of reformulations of strong topological properties in terms of virtual homology, there's an old result of Waldhausen, probably was already known by then, that M is virtually Haken if and only if the virtual second betti of M is positive. Okay. By Poincare duality, this is the same as the virtual first betti number. And to fully explain the analogy, a Haken three-manifold is a manifold that contains a pi1 injective embedded surface, or incompressible embedded surface. Sorry. And there's an analogy of this result in a combinatorial setting that we care about, because such G, a hyperbolic fundamental group of graph of free groups, cyclic edge subgroups, such G contains a surface subgroup if and only if the virtual second betti number is positive, which is quite a surprising analogy between the two cases. But here, of course, I'm hiding part of the story. This result, so Calegari states one direction, and the other direction really follows by things that were known by then, local quasi-convexity of G and so on. But I mentioned some of such results before. Another example from three-manifold topology is that, in fact, M has positive first betti number, virtual first betti number, or equivalently, virtual second betti number. They prove much more, and there's of course many people involved, like Bergeron, Weiss, and so on. But the point I want to make is that again there's an analogy with the groups we care about that says that if G is not free, then the virtual second betti number is positive. Okay. Although we should say story in this case goes in a different way, because in order to prove this, this is a corollary of Wilton methods, where he ensures a surface subgroup. And then as a consequence of this surface being seen in some finite cover, he produces second homology in a finite cover. Okay, so basically maybe now I should say this is the only way we have to produce second homology in finite covers of subgroups, say for this two-dimensional example G, or for three manifolds, which is producing surface subgroups and hopefully seeing them in finite covers. Right, okay, they prove much more, as I said, that if M is hyperbolic, then in fact they are large, so they have infinite virtual first betti number. The same, actually, Alan Reed told us about this. The same holds in high dimension for arithmetic manifolds of simplest type. But the question now is, what about G, right? We know by Wilton's result that the virtual second betti is positive, as in three-manifold topology. But it's not clear if being positive is the same as being infinite. Or, yeah, or when it is the case, right? Because for surfaces, it will not be infinite, it's just positive, right? Okay, so with this question, we can move on to the next slide, which are actual computations of virtual homologies for groups G as before. Okay, we can also address residually free groups, and this is because they are very close to the second family, with the one I introduced before, by Sellas hierarchy, right? Limit groups have a finite hierarchy, where the first step of the hierarchy is kind of these fundamental groups of graphs of free groups. So the methods are essentially the same. We should think of the second case, basically. And then residually free groups, embedding products of limit groups, so you can do similar stuff. Okay, on the one hand, relating the virtual second Betti number, we prove that if this is finite, then it's only because of the obvious examples. G has to be free abelian, free, or a surface group. And otherwise, there are just many surfaces inside, independent from each other in homology or independent algebraically, in the sense that we have free products of many surfaces, and this sort of blows up the virtual second Betti number. Then on the relating higher homological invariants, we can prove that if, well, let k be greater or equal than 3, if the virtual kth Betti number is finite, it's either, okay, for homological dimension reasons, namely that the homological dimension is smaller than k. Right? Or the reason is because G is just free abelian. And there are no other examples, basically. Okay, one way to read this theorem is that if you have a homological dimension k, you will have a flat dimension k. But in fact, if you're not abelian, you will have many of those flats, which blow up the virtual homology in that dimension, basically. Sorry, I got very cold in a very stupid way, and I hope I can finish the talk, but it's getting complicated. Okay. Are there any questions for? Okay. Now we're going to focus on, before giving some comments about the proof, I'm going to focus on some consequences of this. One consequence is that we can get the conjecture of Melnikov under the very strong assumption that G is residually free. Okay, so if our one related group is residually free, which is very exceptional, we can conclude that G's the only examples are just free or surface groups. Yeah. The reason is we know by Lindon's asphericity, for example, what is the second homology of one related groups, and it's always zero dimensional or one dimensional. So if the virtual second Betti number is infinite, it's by the previous theorem because G is free or surface. Okay, and a second consequence of this is for manifolds of higher dimension. which okay, under the additional assumption that the fundamental group is residually free, we can say something about how they are virtually. So okay, the setting is similar as before, closed spherical manifold, dimension n, at least 5. And if the fundamental group is residually free, it's because M is virtually a product of the obvious examples. So these are circles and closed surfaces. Okay. The reason for this is we saw in the previous slide that having finite virtual betti number for the top dimension of a group is very specific to free abelian groups or surfaces. And so using a lot of results on structure of residually free groups, we can get this virtually. And of course, we also use the solution of the Borel conjecture by Bartels and Luke. Okay, and in addition, we can get an alternative approach to a result that is originally due to Wilton, namely the Remeslenikov conjecture for the case when G is residually free. Okay, I think I have 2 more slides. Are there any questions before? Excuse me with the stops, because otherwise I feel like I'm going to die. Okay, so now I want to talk about how to prove that if a group like this, okay, just cyclic amalgamation of 2 free groups, if it is not free for a surface, it has infinite virtual second betti number. Okay. Let us first recall that Wilton showed that if G is not free, then there is a surface subgroup of G. Okay. And this is how, in combination with the virtual retractions properties of this group G, he can get that the virtual second betti is positive. Okay? The argument is just that okay, in some G1, G1 retracts onto the surface. The retraction induces a retraction at the level of homology. So we see the homology of the surface in G1. So the strategy when G is not a surface, okay, when G is not a surface, we claim we don't only get positive first, second betti, we get infinite. The strategy when G is not a surface is to upgrade the argument of Wilton to get free products of surfaces inside. If we get a free product of 2 surfaces, then by the same argument, we get the virtual second betti number is at least 2. The betti number, the second betti number of the free product of 2 surfaces, right? And right, and you can do this for more free products of surfaces. I should comment the reason why these homologies are also seen in the profinite completion is by this notion of Serre of homological goodness. So this is what's hidden behind the applications to profinite rigidity. And then if you want to prove the analogous result for just higher virtual betti numbers, instead of doing this trick with surfaces, you do it with flats. Okay, so if you are not free abelian, you will have a flat of top dimension, which captures your homological dimension. If you're not free abelian, you will have many of these. And in fact, free abelian groups are always elliptic with respect to these splittings, because they are 2 acylindrical splittings. So So you see the free abelian groups in vertices of splittings, and by my aviators, you can control as well what happens. Okay. And lastly, this is the last slide, I wanted to mention something about the growth of this second Betti number, because we have proven that if this group G is hyperbolic and is not free or surface, we have proven that the virtual second Betti is infinite. But something that is not clear at all is basically what is the growth? What is the growth of these second Betti numbers? We only know, in fact, you can take a chain of finite index normal subgroups such that second Betti number goes to infinity, but we don't know how fast it grows, right? And from the method, it's not difficult to see there is a constant C, which only depends on the group G. There's a constant C such that, for all n, you can take a finite index subgroup Hn with index not very big, meaning in the measured by n, and with second Betti at least n. So if you want to go to a finite index subgroup whose second Betti is at least n, you need roughly index at most n. But by Luke approximation, this is where I'm going to finish. By Luke approximation, we know that those super fast growing second Betti chains are never going to be have trivial intersection, because by Luke approximation, we know that the limit of these things divided by the index are always zero, because that's the second Betti number. Okay, so it's still unclear what is the exact growth, depending on whether the chain has trivial intersection or not. But those are other questions you can ask. Okay, thank you. So.
Okay, thank you. Does anyone have any questions? So I was wondering if your theorem didn't incorporate Bom's-like solitary subgroups. Is there any way, do you think, of what do I mean? Is there any way of getting more than two generators in your theorem, if that makes sense? So you had the theorem that a one-relator group, a Melnikov one-relator group that's also virtually free, residually free, is a free group or a surface group. If you were to relax virtually free, residually free, you also need to somehow bypass Bom's-like solitary subgroups. Is there any way of doing that you could see?
Sorry, I'm not sure I got the question about this weak form.
So the theorem is, so if you relaxed residually free to residually finite, your theorem is false because of Bom's-like solitary subgroups. Can you see of any way of assuming more than two generators in your theorem, if that makes sense?
So the question is, can I see there are no, in the general case, can I see there are no Bom's-like solitary subgroups in G? Sorry.
How would you? So how could you? Can you see a way of using this result to prove the Melnikov conjecture?
Okay, yeah. No, I wouldn't say so.
Okay.
You would need first to to understand much better what is the one relator hierarchy of G. And basically all these tools about getting second homologies and getting surface subgroups just work for cyclic hierarchies. So I think that, yeah, there are very strong limitations for all these methods. So this is not really, I wouldn't say this is a curiosity. I wouldn't say this is a step forward for the conjecture in any way.
Okay.
Yeah.